Welcome to the Explainer. Have you ever just stopped and wondered how your phone, your laptop, even your smart coffee maker, how it actually thinks? How does it make all those tiny decisions every second? Well, today we're going to pull back the curtain and meet the incredibly simple little decision makers that are hiding inside every piece of technology you own. So here's the plan. We're going to start with the super simple language that all digital stuff uses to make decisions. Then we'll meet the three most important logic gates, kind of like the primary colors of computing. After that, we'll check out their opposite siblings and one really special exclusive gate. And finally, we'll tie all these tiny little pieces together to show you how they create the powerful gadgets we use every single day. All right, let's start at the very beginning. What's the fundamental idea that makes any of this even possible? So let's just ask the most basic question of all. When you press a key, you tap your screen. How does that machine, that chunk of metal and silicone, actually know what to do? How does it make a choice?
Well, the answer is this thing called Boolean logic. And honestly, it is shockingly simple. See, inside a computer, every single piece of information can only be one of two things. It's either a 1, which you can think of as on or true, or it's a 0, which means off or false. That's it. Every complicated thing your computer does just boils down to a gigantic chain of these simple yes or no questions.
Okay, so if everything is just a 1 or a 0, how does a computer actually do anything with them? That is where we meet the real building blocks of all logic, the fundamental gates. You can think of them like the primary colors of the digital world. Every other fancy operation is just some kind of mix of these three.
First up, let's look at that diagram at the very top. This is the NOT gate. I like to call it the ultimate rebel because it has one single job. It takes whatever you give it, a 1 or a 0, and it flips it to the exact opposite.
And this little chart, it's called a truth table. It shows us exactly how it works. It's so simple. If you put a 0 in, you get a 1 out. If you put a 1 in, you get a 0 out. That's all it does. It just says, not this.
All right, next up, let's look at that middle diagram. That's the AND gate. The best way to think about this one is like a really strict bouncer at an exclusive club. It's got two inputs, and it will only, and I mean only, let a 1 out the other side if input A and input B are both 1. If even one of them is a 0, sorry, you're not getting in.
And its truth table proves it, right? Just look. The first 3 rows, they all end up as 0. The only way you're getting a 1 out of this thing is that very last row where both inputs are 1. The bouncer's rule is the law.
Now, our third fundamental gate, that's the one at the bottom, is the OR gate. Now, if the AND gate was a strict bouncer, this one's the easygoing friend. It's got 2 inputs too, but its rule is way more chill. If input A or input B is a 1, then the output is a 1. It's happy as long as at least one of them is true.
And if you look at its truth table, you can see exactly what I mean. The only time you get a 0 is that very first row, when both inputs are 0. Any other time, as long as there's at least one 1 coming in, you're going to get a 1 coming out.
Okay, so those are our 3 primary colors, NOT, AND, and OR. Now, this is where it gets really fun, because we can start combining them to make new gates. So let's meet the opposite gates, which are really just clever mashups of the ones we already know. Now check this out. It's all in the visuals. On the left, there's our friend the AND gate, but on the right, that's a NAND gate. And you've got to see that tiny little circle at the pointy end of the NAND gate. In logic diagrams, that little circle always means not. So a NAND gate is literally a not AND gate. It does the AND thing, and then it just flips the result.
And the proof is right here in the truth table. I mean, look at it. It's the exact opposite of the AND gates table. Remember how the AND gate only gave us a single 1? Well, the NAND gate gives us a 1 in almost every case. It only gives you a 0 when both inputs are 1.
And you can probably guess what's coming next. It's the same pattern. Here we've got the OR gate right next to the NOR gate. And, yep, there it is again. That little circle tells you the whole story. A NOR gate is just a not OR gate. It does exactly what an OR gate does, and then it flips the final answer.
And sure enough, its truth table is the direct opposite of the OR gates. The only time a NOR gate ever gives you a 1 is when both inputs are 0, which is, the one and only time that a regular OR gate would give you a 0.
It's a really cool, simple symmetry. All right, we have just one final gate to meet. And this one has a very specific and a really powerful job. This is the exclusive gate.
This is the XOR gate, and XOR stands for exclusive OR. Its rule is basically right there in the name. It will only give you a 1 if one input or the other is a 1. But, and this is the key, exclusively one or the other. It can't be both.
Its truth table really makes this special rule obvious. Look, the output is only a 1 when the two inputs are different. If the input's are the same, 2 zeros or 2 ones, the output is 0. This thing is basically a difference detector, and that function is absolutely essential for things like computer math. It's how machines add numbers. So we've met the whole family, but the big question now is, so what? Right? Let's connect these simple little gates to the amazing gadgets we use every day. Just take a second and look at this number. 2 billion with a B. That is how many of these tiny little logic gates, built out of microscopic switches called transistors, can be jammed onto a single computer chip today. Billions of them on a little sliver of silicon smaller than your thumbnail.
And here it is. This is the crucial point. Every single thing you do on a computer or a phone is built out of these 6 simple decisions. That game you're playing, that website you're scrolling through, the app you just opened, it is all just billions and billions of these simple not, and, or, and XR questions being asked and answered over and over at almost the speed of light.
And that's really the amazing secret, isn't it? All of this incredible, mind-boggling digital complexity is built on a foundation that's actually truly simple. So I'll leave you with a question. Now that you know the secret language of computers, what will you build with it?